Tonight, Enlighten welcomes NASA Jet Propulsion Laboratory Solar System Ambassador Ward Yohe, who will be presenting the solar system and beyond with information and images depicting past, present, and future exploration of our solar system. In addition to Ward's passion for space, he loves hiking, camping, backpacking, biking, snowshoeing, and kayaking with his wife Sharon and other friends. He considers Washington's Salish Sea region to be one of the most fantastic spots on the planet Earth. Ward grew up in Big Run, Pennsylvania, and graduated from high school in nearby Punxsutawney in 1989. He then attended U.S. Naval Nuclear Electronics, Power, and Prototype schools, and served as a nuclear reactor operator on the USS Truxtun, home ported in Bremerton from 1991 to 1995. Ward is currently the technology project manager at the University of Washington's Medical Center. Now remember to put all your questions for Ward in the chat room, and please help me welcome Ward Yohe.
Well, thank you for having me, everybody. I'm going to dive right into it. I've got a lot of material to cover tonight, and I'm going to go ahead and share my screen here. Hopefully, everybody can see that okay.
Yes.
That's good. So, all right. Okay, so as per my introduction, I'm a volunteer solar system ambassador with NASA's Jet Propulsion Laboratory. This is a very neat program. It's been around for 25 years now. There's several hundred of us across the country. We all do something a little bit different. We have support from the Jet Propulsion Laboratory. We can join forums with scientists working on certain projects, but we also have quite a bit of latitude. Some ambassadors are amateur astronomers and do star parties. Some focus on robotics, some on astrobiology. I kind of like to do a summary of solar system exploration. So I tap into many different resources and try to kind of give you a quick snapshot of what we're doing. Again, it's only an hour, so there's only so much I can talk about, but just know there's a lot of activity going on in space exploration, both with NASA and our international partners. So there's a volunteer effort I do. What I do for a living, a technology project manager in UW Medicine. I work on things like our enterprise-wide nurse call system transformation, portable equipment asset tracking. I do that at multiple of our hospitals. UW Medicine's a pretty big organization. I'm directly employed by UW Medical Center, and most of my efforts are at our Montlake campus, but I also support our Northwest campus as well. I live in Bremerton and I commute over to Seattle via foot, bus, ferry, and light rail. So we're going to take a hike through the solar system today. We're going to start over here with the sun, which you can't only see a little bit of in this picture. We're going to work through the inner planets, the outer planets, and a bit beyond. Everything we talk about today is going to be information we've learned from a wide variety of missions. And like I said, just know for every mission I talk about, there are dozens and dozens out there that I can't even touch. If you go to nasa.gov, you can actually get links to almost every mission NASA has ever been part of. So we're going to start with the center of our solar system. The center of our solar system is the sun, our star. Our sun is a star, just like all the other stars in the night sky. It's an average sized star. Some are much, much bigger than our sun. Some are much smaller than our sun. But all the rest of the stars in the sky are quite a bit further away than our sun is from us. And we'll talk a little bit more about that in a minute. Kind of stars 101, how stars form in the universe. And we see this happening at different stages all over now that we've gotten to look pretty deep into our own galaxy and neighboring galaxies. Basically, you get enough hydrogen all in one place, like a lot of hydrogen, which is the most common element in the universe. And the gravity from it eventually gets it to a point where it all starts pulling together. And then you finally get to this critical point where nuclear fusion starts. And nuclear fusion is when you have two atoms that collide and they combine and they become a different element. So that hydrogen becomes a different element, and some of the mass of those two original atoms turns into pure energy. So that's the light, the heat, the radiation that comes from the sun. So that forms new elements. As time goes on in stars of different sizes, other elements form, sometimes not till very much later in the life of the star. And so the iron in your blood formed inside stars, the calcium in your teeth formed inside stars, all the elements around you, copper and zinc and just everything, lithium, formed inside stars. Stars are the element factories of the universe. And we, again, get to see this. We sometimes see a star explode and we see all of a sudden a new set of elements coming out of it that we didn't see before because they were just very recently formed. So I say our star is average size. It's still big. It's still really big. 1,000,000 times the volume of the Earth, 109 times the diameter of the Earth. So we're going to talk about some pretty big distances, pretty extreme distances and sizes today. And I kind of want to try to put this in perspective as well as I can. So I'm going to take in and try to make a scale model of the solar system for you. When I'm in a school or in a building, I've tried to come up with something, kind of did the calculations to come up with something that I could talk about in a room I'm sitting in. So I'm going to use a tennis ball to represent our sun. So this is our star, center of our solar system. That's our sun. Now, I need something to compare it to. So I'm going to take this piece of paper here and I'm going to make a spit wad. So there's a little tiny spit wad. So that represents the Earth. So there's the sun and the Earth size to scale. For that size, we also need to get the distance right. They're actually 93 million miles apart. So I got to break out. The handy tape measure here and measure about 22 feet. So in our small house, if I put the tennis ball over here by this window, let's see here, about there, I have a short hallway that goes down our hall to our bathroom, and I would be putting the spit wad right at the edge of the bathtub. So in our small house, that would be our 22 feet apart. So that's size and distance to scale, Earth and sun. To give you another feel for that size comparison, if this is the sun, then this is the Earth in our solar system. The sun makes up about 99% of the mass of the solar system. Don't mean to make you feel small and insignificant, just a consequence of the laws of physics here whenever we look at these sizes. So the sun, again, it's the core of our solar system and has so much mass, everything orbits around it. And we'll learn today that everything's in motion in the universe. Everything is either orbiting something or heading to something else, and gravity is just playing this dance everywhere. And it's quite remarkable. Nothing just sits still. So the sun gives off all this great stuff, right? It gives us light, it gives us heat, photosynthesis. We would not have food to eat if we didn't have our sun providing these wonderful things for us. But it also gives off a lot of particles that don't ever make it to the Earth because of our atmosphere and magnetic field, which we'll talk about in a little bit. So we built a spacecraft to go up and study the sun in a different way. And I'm going to say we, as I said, I'm a volunteer with NASA. I've never built a spacecraft. I'm not even a scientist. I'm not an engineer. When I say we, think of it more as those that work at NASA and really people that are paid by your taxpayer dollars and the contractors that build these things. And really almost every effort we do that's successful has a lot of international collaboration. Almost nothing is just one little silo. So whenever I say we today, just insert the word humanity. So we equals humanity for today's talk. So when we, humanity, decided to build the Genesis spacecraft, named such because we were going back to look for origins from the sun. So this is pretty typical of most spacecraft we'll talk about today. The center part here where the computers and science instruments and communication gear are pretty small. They would fit this room I'm in, this office I'm in is about 8 by 8 feet. So that core of the spacecraft would fit in this room. And then the solar panels, which fold up for launch and extend out, would be about the length of my house, about 30 feet long. So that just to kind of give you a feel for the size of it. Now to get something that size into orbit, takes a huge rocket. This is the launch of Genesis. The spacecraft itself is tucked away up in this nose cone. This is a 200-foot high rocket, a 20-story high rocket. Over 90% of it is fuel. It'd almost be like if you're driving a car and you had a tanker truck as your gas tank. And the reason you need so much fuel is because getting into space is all about speed. You know, we think about going high to get into space. You also need to go fast. 17,500 miles an hour is your minimum speed to get into orbit, 30 times the speed of a jetliner. So when we launch, we gotta go fast. In the United States, we usually launch from Florida. A couple reasons for that. One, we want to fly out over the ocean in case there's an accident, or whenever some types of rockets, when they run out of fuel, the boosters fall away. So you want that to happen over an ocean instead of over land. But the reason we picked Florida is because it's close to the equator. And that's, again, all about speed. So you think about it, when I'm here on the Earth, if I could stand on the North Pole, I'd actually stand on the South Pole because there's land there. If I stood there, right, what would I do in one day? I would just spin around once in place. But if I'm here at the equator, if I'm close to the equator, well, the Earth is 25,000 miles in circumference around. It rotates once every 24 hours. So with respect to space, at the equator, you're going 1,000 miles an hour already. So you can use that to use less fuel or to take a larger cargo. You know, I know there's folks from Pennsylvania watching this, my family, us in Washington, we're further up north. Here, we're going about 800 miles an hour. So if the Earth stopped rotating right now, it won't, but if it did, we would fly out of our seats at 800 miles an hour. Everything would be. The air around you is moving at 800 miles an hour. Your body is, everything is. Everything's in motion. So exploring space is really difficult. The Genesis mission was 99.9% successful and pretty much a complete and utter failure. The rocket launched perfectly. The spacecraft deployed perfectly. The spacecraft operated out in space for years. The sample system worked great. It collected these particles coming off of the sun, managed after years, put them in a capsule, came back right on target to come back to Earth, went through the atmosphere just as designed. The heat shield worked great, and then the parachute didn't open. The parachute that was supposed to gently set it down, and instead of gently landing on the ground, it went smashing in the desert at very high speed, destroyed most of the samples. They were able to extract some science out of it in the end, but it was pretty hard. But the reason that failure happened was because one technician put one sensor about that big in upside down. And that was the sensor that sensed gravity and initiate the parachute deployment. And we all know that it wasn't just that, couldn't have been just that one technician, right? There's cross checks, there's team efforts. You know, I work at a hospital. We are so keen on being able to have everybody speak up. You can't have 1% of surgical sponges left in a liver transplant patient and have a good medical outcome. That team that's working on it everyone's got to be able to say, hey, I think we need to double check our list. I think I'm missing a sponge. Whatever they need to do to have success, it takes that teamwork. So in cases that are successful, is a mission like the SOHO. SOHO was launched a long time ago, has operated way longer than it was designed to. And it's a mission designed to study space weather. So we talk about the good things that come from the sun, right? Heat, get light. We can generate electricity with solar from the sun, but also it sends off some pretty bad stuff. Let's remember the sun is a gigantic, continuously exploding nuclear fusion bomb on an immense scale. So there's these huge storms happening on the sun, and they go in cycles. And sometimes those storms come and aim at the Earth, and they can affect our satellites. You know, we're so dependent on satellites now for internet coverage, for GPS. Like, you know, there's people that couldn't find their way on a paper map anymore, unfortunately. Emergency beacons for ships at sea. There's just so much we depend on our satellites for, and they can be very vulnerable to these hits. Likewise, even on Earth, we can be affected. The big thing about this picture is in the red circle, what you don't see, and this is taken in 1989, that should be the intense lights of the greater Montreal, Quebec area. But instead it's dark. Millions of people were in the dark because a solar storm hit the Earth and actually fried transformers and caused a massive power outage. There have been bigger events. Well, to give you a little feel for how big these are, okay, we know this distance is not to scale because we just did our scale model of the Earth and the tennis ball and the spit wad. But the size is to scale in this picture. So when a coronal mass ejection this big is heading towards us, we'd like to know about it. There was one of these in 1859 called the Carrington Event that was pretty significant. Carrington, these are drawings that he made looking through a telescope at the sun. And by the way, never ever look at the sun through a telescope unless you have the proper one. You can literally burn your eyes permanently, go blind. But if you have the right filters and the right telescope, you can look at the sun. He couldn't take a picture of it because they didn't have that technology yet, but he drew these sunspots, and they were huge, bigger than anything he had ever seen. So he drew this, and a couple days later in London, they detected this huge deflection in Earth's magnetic field on a magnetogram, and it was what became known as the Carrington Event. It was so big that it took out telegraph systems all over the world. So you can picture sitting there using Morse code like my great grandmother did in the early 1900s, and all of a sudden your equipment stops working. In some cases, it caught on fire because the surge of energy from the sun was so big. So probably your first thought in 1859 isn't, wow, there must have been a storm 93 million miles away in the sun that just set my building on fire. But that's exactly what happened. And that's not just a once in every 1,000-year kind of event. Just a couple years ago, a storm almost identical to the Carrington Event missed Earth by 1 week, aimed straight at us in orbit. We watched other ones hurl off in other directions from the sun. Sun's a sphere, so they can go any direction. But this one was headed right for the Earth, and we missed it by a week in our orbit. Had we hit it, we probably wouldn't be having this conversation over Zoom right now because our electrical grid would probably still be undergoing reconstruction. There'd be trillions of dollars of damage. It would just be crippling to any modern economy. So again, we like to keep an eye out for these things. So we're worried about them, but there are things we can do because we have satellites up there monitoring these storms. If we can predict that they're coming, and some of these you actually have a couple days notice. It's not at the speed of light. You have a little bit of time to respond. We may do things that it would not be surprising if your local power company at some point said, hey, we're turning off all power in your area, just like they do for wildfires in some cases now. So we can make sure our transformers survive this inevitable storm that's going to hit, so we can turn them back on when it's over. Kind of like the old days of unplugging your refrigerator during a lightning storm without a surge protector. So those are things we might do. We might have to think of having backup transformers in place to install because they take so long to manufacture, backup satellites to quickly restore at least basic GPS coverage. So all those kinds of things are being seriously considered, and we're studying space weather more and more. This mission, Stereo, used binocular vision, and just like when I was a kid and used a Viewmaster to looking at a 3D picture, basically the way your brain puts that together, you take a picture of the same thing from two angles, and then with the colored glasses, you can actually reassemble that in your mind. Well, we did the same thing, but these two cameras were tens of millions of miles apart on opposite sides of the sun, watching those waves go across space so we could better predict that space weather. A discovery this mission made on the surface of the sun was pretty fascinating, though, too. We discovered there are tsunamis on the sun. So a tsunami on Earth, it's a big wave, a wave of any size, that's not caused by wind, but by displacement, a mudslide, an earthquake, something like that. If you drop a pebble in a bucket of water and watch the ripples go out, you've just made a small tsunami. Well, the same thing happens on the sun. There's no water on the sun. There's 10,000 degree plasma surface, but sometimes those solar storms will generate a tsunami. And so here you're watching the wave propagate out just like the pebble in the bucket. And if you could stand here, you can't obviously, but if you could stand there, you'd be watching a tsunami of solar plasma coming at you, a wave 8,000 miles high, a wave as tall, almost as tall as the Earth is wide. So pretty extreme weather happens on the sun. We've built this Parker Solar Probe to go study the sun like never before, closer than we've ever done. And it's amazing. It's actually flown It uses a complex set of orbital maneuvers, and kind of when you do planetary flybys, you can actually use the gravity of a planet to alter your course, speed up, slow down, adjust things. And it's very tricky, but without using these kind of planetary effects, you couldn't even make these missions. You couldn't carry enough fuel to do what you need to do. But you got to see how hard the math is to do on this. You can see the clock ticking there. They're projecting out years in advance exactly where Venus and Mercury and this are going to be, the spacecraft, the speed it's got to come in, the angle, the timing, and they're like, no, this is the day we're going to fly by Venus again to get another boost to adjust our trajectory. This is a picture taken from inside the atmosphere of the sun by the Parker Solar Probe. No one had ever done anything like that before. Here's a picture taken just a little over an hour ago by the Solar Dynamics Observatory up in high Earth orbit. And that's what our sun looks like right now. And, on the surface, again, the sun is just a very dynamic place. There's magnetic field lines always connecting and reconnecting. And here's a view from today in a little different wavelength, an ultraviolet. There's what are called coronal holes here. And this is not terribly uncommon, but the stream of particles coming from these two holes will hit the Earth this weekend. So don't worry, our planet's ready for them. This happens frequently, but it's something we watch on a routine basis to see how strong they are. So now we get out to the planets. Closest planet to the sun is Mercury. So Mercury is much closer to the sun than the Earth, so you'd figure it'd be hotter than the Earth, right? And sure enough, it is 332 degrees Fahrenheit, 167 Celsius, hotter than boiling point of water on Mercury. However, average temperature on Mercury is a little bit deceiving because a day on Mercury is actually longer than a year on Mercury, and that's so a day on the Earth is 24 hours, right? One rotation of the planet. A year on Earth is 365 and 1/4 days, one orbit around the sun. Well, Mercury orbits around the sun every 88 Earth days, but it takes 176 days to rotate once. So one side's always really hot and one side's always really cold. We sent the Messenger spacecraft, did an amazing job. First planet spacecraft to ever orbit Mercury and mapped the entire surface and discovered frozen water deposits in these shadow areas that we would have never expected before this close to the sun. There's another mission on its way there now. It's a joint European-Japanese mission, and it's going to study just all different kind of new perspectives on Mercury. You'll see, we send a spacecraft to a planet, and then new tech. Well, we almost always come up with more questions than answers. So we head there to solve a specific problem, and we're like, oh, we hadn't even thought to ask that before. And then new technologies make you able to do more with a smaller spacecraft or better computers or what have you. So it's kind of a recurring theme to keep kind of going back and visiting some of these same objects years later. Venus, further from the sun than Mercury. The scientific community figured that Venus would be cooler than Mercury. In fact, they figured Venus is about the same size as the Earth, and it's just really in celestial terms, just a little bit closer to the sun than the Earth is. So they thought it would be kind of a tropical, just a more tropical Earth, but they were way off. It's super hot on Venus, 867 degrees Fahrenheit. That's like almost twice as hot as a pizza oven. So super hot, and we study the universe because we're curious people, right? We want to learn as much as we can, but sometimes we also learn things that have applications where we live and help us understand things. And one of those is this. What makes Venus so hot is this CO2. It's got a really thick carbon dioxide atmosphere, 90 times as much pressure as Earth's atmosphere. And so kind of seeing what happens on Venus, we understand the basics of how CO2 works. And it's just the basic physics of the molecule. Carbon dioxide, brings in sunlight, and then it ends up sends some heat back out to space, but it sends more down and traps it. So basically, enough carbon dioxide acts kind of like a blanket around an atmosphere, and we've gotten to see that in spades on Venus. Lots of missions have gone to Venus, especially in the early days of the space race with the Soviet Union. Orbiters, some atmospheric missions, but landing on the surface, only a couple of spacecraft have done that, and they were destroyed within an hour. It's just, again, that high pressure, and then there's and it also rains liquid acid rain, so not a very pleasant place. Venus is also covered in clouds, so you can't see the whole surface. You can't see any of the surface with just a regular camera. So in the 90s, we sent the Magellan spacecraft, and it used radar to map Venus. And at the end of that mission, we actually had better topographical maps of Venus than we had of Earth at the time. And that same technology we brought back, and now when you look at your Google map and go to look at elevations, it's so accurate, and a lot of it's that technology that built off this and similar missions. Japan has a spacecraft in orbit around Venus right now, and when it was on its way there, it also released a solar sail experiment. And the idea of a solar sail, just like a sailboat on the Salish Sea uses wind to push the sail to propel the vessel, in this case, you have a super thin, really big, lightweight sail that solar particles hitting it can actually give it just the tiniest bit of thrust, a very, very little bit of thrust, but it keeps doing it continuously, as opposed to a rocket engine that burns for a brief while, then runs out of fuel. So we might actually be able to use solar sails to go out and more inexpensively explore the outer solar system in the future. And there's even some experiments happening in Earth orbit right now. So speaking of Earth, we get to Earth, next planet in the solar system, my favorite planet by far. I'm guessing it's yours too. Some really special things about our planet. Well, one, 21% oxygen atmosphere. Only place in the solar system I can take a deep breath of oxygen-rich air without being inside, wearing a spacesuit or being on a spacecraft, generating its own atmosphere. Another big one is here, 59 degrees Fahrenheit. We've talked about hotter planets so far, and now we're getting down to something a little more reasonable. Big key to that, my water here in my cup is in liquid state at that temperature. We kind of consider it the Goldilocks zone. We're just far enough away from our star to not be melting, to not have all the atmosphere vaporize, and we're not so far away that everything's frozen, like happens on Mars. We're just at this sweet spot in the middle. In fact, when we look for habitable planets around other stars, which we have found some pretty promising candidates, we're looking for ones that are at that right distance from their star, where water could be liquid. Because as far as we know, all life that we know of needs water. Bacteria, whales, humans, alligators, spiders, everybody needs liquid water. So we haven't found life that doesn't need it yet. So that's what we look for. So those are a couple really important things about our planet. Some of the first things we started understanding about our planet when we sent up rockets was how our magnetic field worked. We had known for centuries that we had a magnetic field because sailors had compasses with a needle that pointed north. And the reason we were pretty sure of what's happening is that we have a molten iron core in the center of our planet. And the whole planet's still cooling down from its original formation. There's still all this energy there, and there's radioactive energy in there from the decay of uranium and other things too. So there's all this heat, there's this rotating magnetic core, and it generates this magnetic field. We're lucky at the age of our planet that we still have this heat and we have this magnetic field. Mars doesn't have much of a magnetic field at all, and most of its atmosphere has been blown away by the sun. So our magnetic field holds in our atmosphere and enables us to breathe that oxygen. You see basically the way that those magnetic lines form, it's kind of a force field. These are called lines of flux. They go from pole to pole, and they're protecting us from that solar storm, but you can see just at the poles inherently they're thinner, just kind of the way it works. And so that's when you can get these effects, the auroras, the northern and southern lights. Normally you have to be pretty far north or south to see them, but whenever there's big solar activity, it can move down to Washington, to Pennsylvania, even to California. And basically this is the interaction of that solar stream mixing with our magnetic field and our atmosphere to create pretty amazing light shows. During the Carrington Event in 1859, you could see the auroras in the tropics. Almost the entire planet was lit up with auroras. There's no color pictures of it, of course, but there's lots of evidence and stories of that. And our magnetic field, like so many things, is not rock solid. It moves around. We know in past times in eons, looking at rock records, we know it has flipped direction before. And so many things depend on it. Whales for migration, and humans for navigation. In fact, we've discovered moving around big holes in the magnetic field that sometimes commercial jet airlines have to avoid so it doesn't mess up their instruments. And we also look down at the Earth from all these satellites that you get perspectives you just can't get any other way. You know, a great example, for hundreds, probably thousands of years, there were stories of rogue waves that would show up out in a calm sea, 100-foot wave that comes up. You know, and people thought that those were just sailors telling stories, but then there were ships that disappeared and you couldn't explain it. Well, with satellites, we've been able to look at ocean heights over the whole planet, you know, on a continuing basis. And sure enough, guess what? Every 2 weeks, about somewhere on Earth, a 100-foot wave pops up out of a calm sea. We don't usually know about it because the oceans are so big, no one's there to see it usually, but sometimes they are. And they have some ideas of some places what causes them, and then there's other ideas. It's just a complete mystery of nature. And here's a look down at Superstorm Sandy that hit the East Coast a few years ago. And, you know, you just can't get this perspective, even with airplanes and all the best ground measurements. You really need satellite imagery to see something like this and to predict a path of where a hurricane's going so you can evacuate people or have people prepare and board up their windows and what have you. We also study other parts of our weather, our ozone hole. So the ozone layer is a natural layer of our atmosphere that protects us from ultraviolet radiation. In the 80s, through ground and space satellite observations, we discovered that it was that layer was thinning, and that actually a hole was forming over Antarctica. And this was very concerning because it was letting in more ultraviolet radiation. And we figured out, though, through science and testing, that it was this depletion was being caused by human industrial activity. Actually, it was chlorofluorocarbons, and they were chemicals that were put in a lot of aerosols and most refrigerants, car air conditioners, refrigerators, what have you. So the world kind of got together, both rich and poor industrialized nations got together in Canada in 1989 and said, hey, you know, we're causing this problem. It's going to cost a fortune to phase out those CFCs, but the cost of not doing it is more expensive and more painful than doing it. So we did it. So we got together, banned chlorofluorocarbons, and over a couple of decades, production has gone to almost zero. There's very little CFC production now. The ozone hole has stabilized, and there's even signs that it might be slowly rebuilding itself a little since we stopped adding this contaminant to the atmosphere. First satellite ever launched was Sputnik, launched by the Soviet Union in 1957. It's about the size of a basketball. That really kicked off the space race. Pretty soon thereafter, NASA launched its first satellite, Explorer 1, and the race was on. And then everything we've talked about so far has been robotic spacecraft. The spacecraft we've talked about have just kind of, a lot of them have gone places we can't send people yet, but we certainly have sent people into space. Yuri Gagarin was the first from the Soviet Union in 1961. Alan Shepard was our first astronaut to go up into suborbital space pretty soon thereafter. And, you know, and now we're used to seeing pictures of people doing somersaults and stuff in outer space. Not the case in these spacecraft. They were cozy. They were tiny, tiny things. You just pretty much had enough room for yourself, for you and your partner. I mean, the longest mission on Gemini was like 16 days. Picture sitting that close to someone for 16 days with the door shut. So, so things have changed. For 30 years, we used the space shuttle. The United States used the space shuttle as our primary way to get to space. And it was an amazing machine. Did science projects, launched the Hubble Space Telescope, helped build the International Space Station, did satellite repair missions. But the crew was still limited to a pretty small crew area here in the front end of the spaceship. So over the years, there's been a series of space stations. And the whole idea behind a space station is that you build a bigger, you know, laboratory in space that doesn't have to have heat shields and parachutes and all that stuff. It stays up there. You use your smaller spacecraft to go to and from it. And then you have enough room to actually do experiments and do research. And there's research you can do in space that you just can't do anyplace else. Materials research that, well, in my hospital at UW Medical Center, we have an entire patient unit. We have a couple actually that are dedicated to infusion for both cancer and other treatments. And so for some of those cancer chemotherapy drugs, there's no fast way to get the treatment. So you have to sit there for like 6 hours. You know, we try to give them TVs and comfortable environments, windows and all that stuff. But they still have to sit there for a long time getting their treatment. Well, there's research happening up on the space station from pharmaceutical companies to see if they can put those proteins together in a different way that you could only do in zero gravity, to turn that into just a simple injection that you could just get at your doctor's office. You'd still have the chemo treatment, but you wouldn't have to burn up a whole day for it. So we may have a remodel project here in a decade to change that unit to something else because we don't need it anymore. I hope so. That would be great. So all these space stations, the Soviets built the first. We had Skylab in the 70s. We worked jointly with the Russians on their Mir space station in the 90s. These have all since deorbited. Like all machines, they wear out and are no longer in operation. And they've been replaced by this. And this is the International Space Station. And I consider this a pretty amazing thing. I personally feel that this ranks up there with, the Great Wall of China, the pyramids, the Panama Canal, unprecedented, well, by far the largest spacecraft humans have ever built, over 300 feet long, bigger than a football field. Huge international cooperation. This is a European resupply ship launched from South America, attached to a Russian service module that was launched from Kazakhstan. There's an American laboratory module launched from Florida. This is a Japanese resupply module launched from Japan. There's a Canadian robotic arm. Just an unprecedented sign of international cooperation. And let's face it, like some of the countries working on this don't get along the best on the ground right now, but we kind of set that aside for the human exploration in space because this was a bigger thing than any one country could do on its own. This was the last launch of the shuttle to the space station. And it was always kind of amazing watching the shuttle come in because you're going 17,000 miles an hour compared to Earth, but it's this delicate balance as you slowly come into dock. Here was kind of a day in the life on the space station. This was astronauts out working on what's called the cupola, and they're in a spacesuit. And we think about the scientists and the engineers and the researchers, but it takes so many people to make this successful. The person that worked on sewing the stitching on the glove of that astronaut on that spacesuit had their life in their hand. I mean, outside is the absolute vacuum of space, and it's 200 degrees above zero in the day and 200 below at night. The janitors that kept the rooms clean for their air filtration system so they wouldn't be contaminated have those astronauts' life in their hands. The software engineers that write the programming to operate the robotic arm, astronauts' life in their hands. It takes thousands of people to make this happen. So this cupola is kind of a bay window in space, and this is what it looks like inside. Window ever flown in space, and just amazing to look down at the ground. Just imagine watching Italy glide underneath you 250 miles below at 17,000 miles an hour. And there's a good place to take pictures, like this picture of Space Shuttle Atlantis coming in for its final landing. That's its plasma trail as it came down through the atmosphere and coming in for a nice safe landing to wrap up the Space Shuttle program. We've had a few teachers have flown in space. Barbara Morgan was the first. She had to wait 20 years. She was the backup to Krista McAuliffe on the Challenger, but she finally got her chance to go into space. Great astronaut, great teacher, great representative of NASA. But I want you to look at her hair on Earth, her hair in space, zero gravity. Everything's different in zero gravity. It's fun, but you have to use a lot of Velcro to attach yourself. Washing your hair is a whole different story in space. It's you just have to rethink everything. I've even heard astronauts say one of the most common mistakes they make after they get back from a long mission is, they have a glass of water and they just let go of it and it smashes to the floor because they forgot about gravity. It's like, oh yeah, that's right. I need to use a table. A lot of us, I know lots of people on this call probably have gone tent camping, as I did as a kid and as an adult. Well, space volume of room in space is a big deal. And so we actually sent kind of a tent up to space. You can kind of see the space station as like Legos. It's in fact, behind me, it's a Lego space station model sitting behind me right now. And it's really like that. There are these modules you can move around. In this case, we actually took up a small module. It's relatively, was able to fit in a pretty small spacecraft. And you can see it's like, not much bigger than a person actually, or a couple of people. But then when you inflate it, it gives you a lot more volume. And it's not just a thin material, it's layers and layers of Kevlar and very durable materials. They think this is maybe actually better than a solid aluminum skin to a traditional space module. And here were the first astronauts ever to be inside a space tent. So it's still attached to the space station and they use it for storage. Another cool thing about the space station is you can watch it go over. There's a couple places you can go on the web. I have an app on my phone so I can see when the space station's flying over, and flies over pretty much all the populated areas of the Earth. So several times a month it flies over where you live. And if you get and the timing has to be right, but you get to go out there and you watch, and it looks different than anything else in the sky. You see this bright light, looks like a really bright airplane, but it's moving very differently. And that's actually the sunlight reflecting off the solar panels. And you can see it fly overhead. You can look at that and say, wow, that's like, there's human beings on board. And that's one of the most amazing engineering achievements of all time. And it's flying over my backyard. So you can't say that about the Panama Canal or the Great Pyramids. And here are the 7 people in space right now as we speak in the Expedition 67 crew. There are 3 American astronauts, 1 Italian astronaut, and 3 Russian cosmonauts on the space station right now. I said I give this presentation in various levels to K through, well, maybe 3rd grade through 12, and in any age group. Pretty much I've not found an age limit. But I like to talk to kids about what they need to do if they want to do those great things. Barbara Morgan, the teacher, had to work hard, study hard, and she eventually got to be a teacher, most importantly, and then also an astronaut. We have, and NASA has brought in people from all sorts of different backgrounds through the years. And Charlie Bolden was a fighter pilot in Vietnam, went on to fly the space shuttle, and then became administrator of NASA. And, it's just that diverse background of astronauts. I mean, NASA and all the space agencies of the world want to be successful. And the only way to do that is to tap into a broad, they have to look wide to everybody to get the best of the best for what they want to do. There's my personal hero astronaut is Peggy Whitson. She has spent more time in space than any other American astronaut, over 650 days. And she's actually going to get to fly back up again as the commander of a private mission pretty soon. You're going to stay in space for a long time. You want to make coffee. So the Italians built a zero gravity espresso machine, harder than it sounds. Got to deal with zero gravity and how the water behaves and what have you. On the space station, they recycle urine and sweat to turn it back into drinking water. And that sounds icky, but same thing happens on Earth. We just do it through clouds and rain. And my glass of water here might have some of George Washington's tears in it for all I know. So they just do it a little more closely on the space station. And they're trying to develop this technology to maybe use in some remote areas that are very arid and dealing with drought, so they could maybe have a portable system that could recycle water to help out some pretty remote villages and what have you. Another recycling effort NASA is working on is the refabricator. They've already done some 3D printing in space, but now they're trying to take the packaging material that they need to send up with all these rocket launches are very violent. So you have to have a lot of insulation, a lot of packing, but now they've designed that packing so they can take it, basically stick it in a hopper, turn it into raw materials and make a part out of it. So wouldn't this be neat if this technology made it in our kitchens, 10 years from now, that when you get that package from Amazon, you just dump those plastic peanuts into the hopper and you print yourself out a new blender lid, because that's what you need. It's broken. That's what they're working on the space station now. And on the space station, you get to fly through those auroras rather than over them. So that's pretty remarkable, or rather than looking up at them, I mean. And right now there's 3 Chinese taikonauts, they're called, on the Chinese space station. The Chinese are building out their own space station right now. There's a lot of players in space right now. There's private companies getting involved with just kind of more tourist and research suborbital flights. NASA, whenever they shut down the space shuttle, they went to private companies and found much more affordable and reliable ways to get cargo to the space station through a couple different providers. And that has helped spur things with, like SpaceX is one of those companies. They got a contract from NASA. They wouldn't have made it without that contract. They successfully carried cargo to the space station. They took the money they made from that, and they've developed reusable space launchers. This is Buck Rogers looking stuff that I would have not imagined possible 10 years ago. And now they're doing it, and now it's cheaper for NASA to launch cargo because now they have these reusable rockets. Using the same idea for commercial crew, and these were some of the test flights of Boeing and SpaceX. SpaceX was the first to get up there with a test flight. This was the uncrewed test flight. This had a mannequin, and this little guy, little Earth, flew up there, and this was an astronaut already on the space station. Then in June of 2020, Doug and Bob launched on our first launch from American soil in over a decade, or about a decade. and they flew up, and they also took this little guy from their sons. They both have young sons, and they volunteered this little dinosaur to go up. Trembler, I think his name was. So when they got up in space, Trembler got to meet Little Earth, and now we are routinely sending people to the space station on that SpaceX spacecraft. Unlike the shuttle, they actually land kind of like the Apollo did on with parachutes and at sea, but much bigger capsules inside. And again, they get to reuse those boosters. There's even been an all private mission into space now, which was kind of nice. The completely privately funded, which was always a dream of NASA. They wanted to get these space companies going, sort of almost like airmail helped get the aviation industry going in the early days of flight. They've been trying to give some seed money and then let it take off and do its thing. And this is the first real example of that. It was a completely private mission. And it was a pretty wealthy guy that was able to fund the whole thing, but he also used it as a fundraiser for St. Jude's Hospital. And Haley was the youngest person to fly into space and the first person with a prosthetic. She was a bone cancer survivor who was treated at St. Jude's and now works at St. Jude's. So she did live interviews with kids that were in the hospital going through treatments, and it was very inspirational, as the name would suggest. NASA's working. They know the International Space Station is going to be out in about a decade, and so they're working with private companies to have them build the next generation of space stations, and then NASA would be one of hopefully many customers using those. So NASA no longer, and I still have quite a bit of information to go through, so I know I'm going kind of fast. I apologize for it. I might go a little over my 7:30 here, just so you know, but I'm going to keep marching forward unless someone flags me down. So solar system's got a lot of stuff going on in it. So now that NASA isn't flying the space shuttle, they put that money towards a big new rocket, the Artemis program, the Space Launch System. And again, lots of testing, and now we're down to, and give you a feel for how this is the biggest rocket ever made. It's actually sitting out on the pad right now in Florida. For those of you who live up here, who have been out to Fort Worden State Park in Port Townsend, I tried to do a size comparison here, and my mom who's listening to this has been out there. So get a little feel for the high bluff. It's taller than that highest bluff. And I kind of plopped it down to scale in the camping area. So you can see kind of some trailers there from the satellite picture, but that's about how big that rocket would be if you were looking at it, over 30 stories tall. There it actually is on the pad right now, getting to hopefully fly by the end of the month. It'll be a pretty big step. It'll be an uncrewed flight, but of a crewed capsule going back around the moon like we haven't done in a long time, in partnership with the European Space Agency, who has built the service module. So then we get out to Earth's moon. Again, the spacecraft can get us to the moon. Some things about the moon. We only ever see one side of it. We talk about the dark side of the moon. It's really the far side of the moon, as we're kind of tidally locked with the moon. So as the moon orbits the Earth, it kind of tugs the water of the entire planet around. So with the rotation of the Earth and the tug of the moon, that changes these tides. And for those of you that know Bremerton, and this is the boat shed, you can kind of see the big differences between high and low tide. And sometimes it can be even more extreme than that. We're pretty sure, so the moon's very important to us, more so than you might realize on a daily basis. Pretty sure that the way, from lots and lots of research, that the way the moon formed was in the early days of the Earth probably got hit by an object about the size of Mars, a small planet that whacked basically the Earth kind of out of sync in its spin, and then the Earth blew up, and this other material blew up, and they recoalesced into Earth is now, but then on the moon. And we've learned even from the Apollo missions and looking at the minerals on Earth, on the moon, and what's similar to Earth and what isn't. And so that resulted in this interesting, like basically the Earth and the moon being tidally locked kind of locks us in place. So we have this 23-degree tilt on the Earth that the other planets don't have. Like Mars wobbles all over the place over long periods of time. But that's super important for us to have seasons. So basically the reason we have spring, summer, winter, and fall is because of the moon keeping the Earth in this stable 23-degree tilt. If we didn't have the moon, again, we would be very unstable and civilization would be very difficult. During times when the poles were facing the sun, they would melt completely and the other side of the planet would be freezing cold. Here's an actual photograph taken by the OSIRIS-REx spacecraft of the Earth and the Moon in one shot. I thought it was kind of cool to get an actual photograph of the two together. In the 60s, the Moon was kind of the holy grail. In the space race with the Soviets, there were orbiters, landers, sample return missions. And then, of course, we did indeed land humans on the Moon. The Apollo program safely set down 6 missions on the Moon. But then again, you kind of think, so of all that money and everything we did, we landed 6 landers on the Moon, each with 2 people, and they were there for about 3 days apiece. So, you know, if I took a dozen people and, you know, sent them to Berlin for 3 days and brought them back, could they tell us everything there is to know about Europe? Not even close. And that's about where we're at with the Moon. We really only kind of, you know, stuck our toe in the water. So we went fast to the Moon. There was a big push, but, you know, and I've heard even the assistant administrator of NASA reference this quote about, you know, if you want to go fast, go alone, but if you want to go far, go together. And that's what's happening next. We're working on going back to the Moon long-term to stay with a lot of international partners. We're working at building a small space station called the Gateway that we'll be able to use as kind of a base camp for lunar exploration. We're using some of those private contracts. SpaceX is building an even bigger rocket than the Space Launch System, and this is real hardware sitting down in Boca Chica, Texas. 400-foot high rocket, which if it all works, will be 100% reusable, which will change the game. But NASA has issued a contract to take this upper stage and make a version that's designed to land on the Moon. Looks like Buck Rogers, I know, but it's real stuff. So this is all called the Artemis program, and it's named Artemis kind of appropriately. Apollo, from mythology, Artemis is the twin sister of Apollo, and the Apollo program was our last missions to the Moon. And there's a whole international effort. Lots of countries have signed the Artemis Accords, and this is kind of it's more than just about being part of a mission, but it's a way of working peacefully in space. And there's all sorts of efforts they're doing, from protecting heritage sites like the Apollo 11 landing site to, you know, sharing information with each other, sharing science, you know, trying to minimize orbital debris. Lots of countries are signing on, and that's appropriate. I mean, right now, China they have not signed the Artemis Accords, but they have a lander and a rover operating on the far side of the Moon and have for quite some time now, and have lots more missions planned. And then you get this perspective of Earth that you only get from the Moon. And this was taken by Bill Anders, who lives up on Orcas Island on Apollo 8 on Christmas Eve, 1968. So it was a remarkable look back at our own planet. So now we get to near-Earth objects. Again, I'm kind of looking at my clock here, but the team told me I could go a little bit long if I need to, so I think I'm going to take them up on that. So near-Earth objects are asteroids and comets that come close to the Earth. An asteroid, think of it as a mini planet, chunk of rock, metal, maybe 50 feet across, maybe 50 miles across. Comets, kind of the same idea, but more icy materials and loose materials, and they kind of vent off material when they get closer to the sun, when they get hot. Most of these are way far from the Earth, but there's a lot that come close to the Earth, and some hit the Earth. And we know asteroids and comets hit the Earth. You just look at the Moon with binoculars. It's covered in craters. It's right next door to us. The only reason we don't see all these craters on Earth is because there's wind and rain and volcanic activity and human activity on the Earth that kind of wipes our surface clean over time. But there are some very obvious craters. Meteor craters, the best preserved big crater on Earth, and that's out in Arizona. It's about a mile across and 600 feet deep. And estimated was made by an object about 200 feet across, so about the size of this little research station down here. And it's just, even a small object at huge speeds can cause massive amounts of damage. It's like firing a bullet at a watermelon. Even though the bullet's way smaller, it's going so fast, it blows the watermelon apart. We found even bigger craters. There's kind of the leading theory for what at least played a big contributing factor to the extinction of the dinosaurs 65 million years ago was most likely a comet or asteroid impact. Big piece of evidence is the crater we found off the coast of Mexico that's 150 miles across, and it really matches up with that evidence, and it's very clearly an impact crater. So that would have been something like the size of Bremerton hitting the Earth, so 6 miles across and causing massive damage. More recently, about a century ago, there was a explosion in Siberia that wiped out 1,000 square miles of forest. And that was probably, again, an object, maybe a couple hundred feet across by the calculations, blew up in the atmosphere. this is in a very remote area, but had this happened over London or Washington, D.C. or New York, our modern history would have been impacted significantly, because this would have been like a massive atomic bomb blast. So now we're looking. Now we know this is a threat. We're looking for objects. We're tracking them. But there's even smaller objects. Here was an object that blew up over Chelyabinsk, Russia, just a few years ago. And so, just like with with weather, we now monitor. We have buoys at sea to look for tsunamis. We have radar to look for tornadoes. Well, we're trying to do the same thing with these kind of space threats. And so now we're sending spacecraft up. We're learning what these objects are made of. We've actually fired impactors into comets to see what the insides are like. We brought back samples from comets. We actually, the OSIRIS-REx mission went into orbit around this object, and this asteroid, there's a chance, we don't know enough about its gravity yet, that it may hit the Earth in a few hundred years. We don't know for sure, but we've collected a lot of data, so we can provide that to our great-great-great-grandchildren so they can be ready to maybe be prepared for it. So we're part of space exploration is trying to think ahead many generations and trying to help out people that you might never even know. We've landed on comets now, and we've just a stunning amount of information. We've seen interstellar objects come in from other solar systems, which we had never seen before. And we talk about the threats of these objects, but we also think probably in the formation of the Earth, we probably got most of our water from asteroids and comets hitting the Earth. So without these things, and that's sort of a balance in the solar system, right? There's kind of good and bad from lots of things we encounter. We might be able to use those materials. There's asteroids with tremendous amounts of resources that we might be able to mine, and there could be $1 trillion economy out there, so we could build big space stations and things that could help protect us from asteroids using them as resources. Then we get out to Mars. We're moving further into the solar system. So lots of missions have gone to Mars, huge features. There's valleys way bigger than the Grand Canyon. There's mountains that dwarf the tallest mountains on the Earth. Mars, though, doesn't have that stable moon like we have. They just have a couple of pretty small moons. There's a lot of countries with orbiters studying Mars right now. We have the Curiosity rover is on Mars right now, and getting into Mars is pretty tricky, landing. And the Perseverance spacecraft used the same technology, this sky crane. And so we actually got some pretty cool footage. They effectively put a bunch of GoPro cameras on these spacecraft so we could actually film them as they came in to land on Mars. And here was the picture taken yesterday from the Curiosity rover. You can see its science arm and then its wheels, and then you can kind of see some of the shadows of some of its other instruments. So that's a pretty fresh picture from Mars. And Mars has all sorts of amazing features, little dust storms and avalanches, tornadoes. Sometimes they have dust storms that cover the whole planet. We have an operating helicopter on Mars right now. It's flown about 30 times now, way beyond expectations. And the Chinese have a rover and a lander operating on Mars right now as we speak. And we talk about those a few years ago, a big comet that would have been like one of the dinosaur wiper outers came within very, very close to Mars, 70,000 miles of Mars. That's like 4 times as close as the moon is to us. If this had flown past the Earth, it would have wiped out half of our satellites. They actually had to hide behind Mars to avoid damage. So Mars, lots of missions on the books for Mars. And we're really getting to that point where, people alive now will probably be walking on Mars if all goes well. We talked about the asteroids that come close to Earth. There's also a whole asteroid belt between Mars and Jupiter. And we have sent spacecraft there and studied the 2 largest objects and gotten some pretty amazing mapping from them. Just briefly, as we move to the outer solar system, stretching the time here, I'm going to pick it up some more. So, just about everything we've talked about, except for some of the private efforts, have been funded by our tax dollars. And, NASA's budget is 0.5% of the federal budget. So 0.5% of the budget does all this, all these missions, human, robotic, and NASA is the National Aeronautics and Space Administration. I don't even have time to talk much about the first A, aeronautics. Just know flying is safer, faster, quieter. A quick example, back in the 80s, there was a lot of plane crashes that had to do with what they thought was wind shear, but they didn't know how to predict it or see it. There was a big crash in Florida that killed a bunch of people, and that really got the National Transportation Safety Board working with NASA saying, hey, we got to figure this out. And so some very brave people at NASA put test instruments on a plane, went on board. This was not, a drone. These are people on board, deliberately flying into storms where they deliberately were trying to find these microbursts, they're called, and could have easily crashed the plane, but they were able to develop the instruments that now we use for warning systems on our planes. So all of us have most likely, if we've ever flown, landed, or taken off in any kind of storm on a commercial plane, have been benefited from this, pretty heroic research. Now we get out to the gas giants. We're in the outer solar system. When I say gas giants, I mean just that. Jupiter is a gas giant made primarily of hydrogen and helium, just like our sun. Its average temperature is 248 below zero. So we're getting way out there into space. Remember on our scale model where the tennis ball was the sun and a little spitwad was the Earth 22 feet away, using that same scale, Jupiter would be 116 feet from this ball. So over at the other side of my neighbor's property, probably something like that. It does have solid moons, the Galilean moons discovered by Galileo, large moons. You can see these with binoculars or a small telescope in your back of your house. You don't see them this good, but you see them as dots of light. The Voyager spacecraft in the 70s just made amazing discoveries. This is the great red spot of Jupiter. When this picture was taken, it was about 3 times the size of the Earth. It's still up there, still bigger than the Earth, but it's a hurricane, basically a Jupiter hurricane that's been storming for apparently hundreds of years. The Galileo mission really looked in close at the moons. Even though it's so cold out there, the gravity of Jupiter and its other moons actually move the crust up and down hundreds of feet a day on Io and melt the rock inside and makes it the most volcanic spot in the solar system. Very similar effect happens on Europa, except Europa is all covered on ice, and now we're pretty sure there's a liquid water ocean underneath all that ice, maybe with more water than all the oceans of the Earth. And it's still that tidal force is what keeps it melted as opposed to direct solar energy. The Juno spacecraft is in orbit around Jupiter right now. When it went into orbit, it was the fastest objects humans had ever made. And it doesn't have humans on board, but it does have passengers and the world's first interplanetary space Legos. So this is a school outreach program, and you have Juno and Jupiter or Zeus from mythology, and Juno's the name of the mission, but then very appropriately Galileo, the scientist who first looked at Jupiter through a telescope. So these space Legos are in orbit around Jupiter as we speak, and we get back some pretty darned amazing pictures and angles of Jupiter we've never seen before. That's the shadow of one of its moons. Actually, it's orbiting. That's effectively an eclipse you're seeing there on the side. You've heard a lot about the James Webb Space Telescope, launched Christmas of 2021, and a lot of you saw that it went out and released its first pictures. Amazing spacecraft, biggest space telescope we've ever sent out, orbiting about 1 million miles from the Earth. The big focus is for it to look way deep out into space, look at some of the early universe, galaxies, but also is designed to be able to look at our own solar system. And so this was a picture released pretty recently of Jupiter, and way better than the scientists thought, better resolution and everything. You can actually see the rings of Jupiter, which are like a millionth as bright as the planet. And you can actually see the auroras in this picture. And I just personally think that's a great photo. We actually saw in the 90s a comet break up and hit Jupiter, broke up into pieces, about mile across pieces, and they left scars the size of the Earth. We think Jupiter actually kind of helps protect the Earth by acting almost like a vacuum cleaner. It's more likely to get hit than we are because it's so massive. However, the world is starting to take this seriously. I mean, we talk about how rare a big comet hit is, but in the last couple decades, we saw Mars almost get hit, just barely missed by a comet that came out of the blue. And we saw Jupiter get hit by an object huge that if it hit Earth, it would have been devastating. So now we're actually using the term planetary defense as a real thing. There's a chunk of NASA's budget. There's a planetary defense coordination office. We're working with other countries. We're working with the UN to take planetary defense seriously. And there's a lot of objects, and some of it's just tracking to see what's out there. So there's about almost 2,300 objects now that we know of that could be threatening. None are known that are going to hit Earth yet, but that's why we keep looking, because we keep finding ones that are kind of close. And guess what? Later this month, we're going to actually do a first planetary defense mission. We're sending a spacecraft deliberately into a small asteroid that's orbiting a bigger asteroid, far enough away from that they're never going to hit Earth. Even if we mess this mission up, we wouldn't redirect them to hit the Earth, but we're going to see how much we can move this object. And that's a technique we might use in the future to actually help protect the Earth. So it's again, just like we want to look for other forms of weather, now we're working together on this. And there's actual pictures of it as the spacecraft gets in closer for September 26th impact. And then the Europeans are going to send a spacecraft later to go back and look at the impact to see what the exact characteristics of it were. Saturn, another gas giant, hydrogen and helium again, 308 degrees below zero. It takes 29 years to go around the sun. We all know it for its rings. If you have a small backyard telescope, you can see the rings, not in this detail, but it's still pretty cool to see them. And they're made of trillions of bits of rock and ice orbiting the planet. Saturn does have many moons. The Cassini spacecraft did a huge amount of research. One of those moons is Titan. Titan, it's a moon because it goes around the planet instead of directly around the sun, but it's different than all the other moons in our solar system because it has a thick atmosphere. And so we actually needed to send a spacecraft in to see what it was like down underneath there. So the Huygens probe went in, we took pictures of the surface. So this is taken from 1 billion miles from the Earth. Actually found river channels made of liquid methane. Methane acts like water does on Earth. It rains, makes lakes, rivers. We're building the Dragonfly spacecraft to go there to actually a nuclear powered drone that's going to fly around Titan in a few years. And here's one of my favorite pictures. This was taken by Cassini. So again, 1 million miles from Earth, turns back, aims, the sun is directly behind it. So that's how you get that backlit effect. And in this picture, it's a beautiful picture, but in this picture, you're in it. There's the Earth. There we all are. It's the ultimate selfie. We built a camera, we sent it out 1 billion miles, turned it around and took a picture. So I hope nobody had lettuce in their teeth whenever this picture was taken, because that is our ultimate selfie. Uranus, another gas giant. We're getting out right to the edge of the solar system now. It takes 84 years to go around the sun. We go past the Centaurs, another whole class of objects out in deep space, and then Neptune, ice giant, 164 years to go around the sun, 360 degrees below zero. On our scale model, it'd be 2 football fields away from my tennis ball representing the sun. So there's our solar system that as we know it. I grew up knowing this guy as a planet, Pluto. Pluto has since been reclassified because we've discovered it's part of another whole class of objects called the Kuiper Belt. But planet or not, it's very interesting. Last time Pluto was in where it is in its current orbit, George Washington was 42. So if we lived on Pluto, we'd be celebrating the first anniversary of our country now. So it has a moon, Charon, and we sent the New Horizons spacecraft out to get a closer look. We zoomed in, and we discovered Pluto was more magnificent than we ever imagined. Big frozen nitrogen glaciers active. We think there's an ocean underneath it, all this stuff. We thought it would be a dead world, and it is far from it, at least geologically. So this is Pluto, there's Charon. My wife's name is Sharon, spelled differently, but this is the Valentine you get from Ward Yohe if you're married to a solar system ambassador. It's the Cat's Eye Nebula. It's the frozen nitrogen heart of Pluto, and then Sharon. So I heart Sharon. So isn't it romantic? There's features on Pluto. There's mountains as high as the Rocky Mountains, 10,000 feet high, made of water ice, H2O ice, 10,000 feet high. And it's got an atmosphere, a blue atmosphere like Earth, which no one expected at all. So I said it's part of this Kuiper Belt. Out in this Kuiper Belt of objects, there are we've actually taken the New Horizons, flown by an object 4 billion miles from the Earth, Erikath, to discover, we think it's kind of 2 objects that merge together from gravity. And then there's Eris. It's an object that we actually had to use. We reclassified Pluto because we found Eris, and we found out it was about the same size as Pluto. So we realized Pluto was part of another whole set of objects, not just this oddball planet. And on our scale model, that would make it about a half-mile away from our tennis ball. We'll come back to that one last time. We think there's a planet 9 out there, a big planet, maybe way out there with a 20,000-year orbit. Haven't found it yet, but we've seen distorted orbits of other things. That's how Neptune was discovered. Didn't find it directly. They predicted it would be there and then looked for it and found it. There's an Oort cloud beyond that, where we think those deep comets come from. And then we get out to the edge of the solar system. Our Voyager spacecraft that flew by Saturn and Jupiter and Uranus and Neptune are now out in what we consider interstellar space, and they're still working. 4 decades later, they're still sending back data, which is amazing. And they're discovering new things. It's much more chaotic out there than we realized. The magnetic fields are more bubbly and in these huge forms. And basically, you know, they're at this edge. We talk about the good and the bad, right? So our sun can cause solar storms that can wreak big havoc on Earth and affect satellites. But our sun also is battling with all the other stars in the nearby galaxy to give us this protective bubble. So basically, its radiation hits those stars' radiation and creates this barrier around us. So we're in this wonderfully safe sphere, safe-ish sphere in the galaxy. And so if our sun dialed way down, okay, we wouldn't be hit by a solar flare, but we'd also get over bombarded by cosmic radiation. So the sun is you know, it's that balance of good and bad that keeps us going. So looking back at our solar system, just to kind of get that feel of the size, let's look at Eris. Eris is the furthest big object we know about in the solar system. So on our scale model, again, tennis ball is the Earth. Tennis ball is the sun. 22 feet away, down on my bathtub, is a spitwad that represents the Earth. At that same scale, Eris would be a half-mile away. So just try to picture something in your mind about a half-mile away down the road, a grocery store or something like that. And now kind of think, if we were going to go find the next star, how far away would we have to put it at this same scale? Where would I have to put the next tennis ball? And from Bremerton, the answer to that is Phoenix, Arizona. So I would have to go to Phoenix, Arizona, 1,126 miles away, plop down another tennis ball this size to represent the next closest star to our star. The actual distance is 24 trillion miles, or 4.2 light years, to Proxima Centauri, which means the light from Proxima Centauri, the photons of light that leave it, take 4.2 years before they hit my eyeball. So when I see Proxima Centauri, I see, even through a telescope, I see what it looked like 4 years ago. It's the closest star. Everything else is further away. Some of the light traveling to us took hundreds of years, some thousands, some tens of thousands, some hundreds of thousands. When we look at a telescope, sometimes you're looking back millions or even billions of years of travel just for that light to get to your eye. Our fastest spacecraft would take thousands of years to get even to the next closest star. So we're in the Milky Way galaxy. A galaxy is a collection of stars that orbits around a common point, usually a supermassive black hole. We can't take a picture of our whole galaxy because we're inside it, but we have a pretty good idea of what it looks like, and we're able to look at just tons and tons and tons of other galaxies around us to get a feel for what galaxies look like. As far as a big spiral galaxy, everything we talked about today, our whole solar system, is represented out here at the edge in the suburbs, maybe the rural areas, of a little dot so small you can't see it in this picture inside one of these clouds. That would be our solar system. And Proxima Centauri would be the next little spot over. That's, again, too small for you to see in this picture. So in our galaxy, there's probably about 400 billion stars, and it's about 100,000 light years across. So it takes 100,000 years for light to get from there to there at the speed of light. But even at those distances, there are threats to the Earth. Like, I don't mean to scare people, but I'm just saying, just like every place else we look, there are things we have to look at and deal with together to solve them. So in 2004, we got hit by a blast from a magnetar, which we were later able to calculate and look back and see what happened. And it was this bizarre star called a magnetar that sent a magnetic pulse that traveled 50,000 light years, took 50,000 years for it to get to the Earth. And it actually impacted us. It went through the Earth, it distorted our magnetic field, it damaged satellites. Now, there's nothing we can do to stop that. That's impossible. That's a force of nature. But there's things we can do together. We might be able to, have those backup satellites, power systems, communication with each other for anything we detect, so we can try to help keep our technological societies functioning. you know, we really are in this together. I know that term's been used a lot in the pandemic, but like it's no joke on this planet. That's the deal. You know, those, you know, there's things we might be able to prevent, like that asteroid deflection mission, or we might know where something's going to be and we can move out of the way, or maybe we even clear an urban area because we know there's going to be an impact, or we prepare for those solar storms. And then, you know, also settling other places in the solar system is maybe a good long-term plan. You know, for those of us that have worked in emergency management, we don't have any of these resources. There's no interstellar FEMA or, you know, any outside source, no Star Trek Enterprise coming to save the day for us. You know, we are in it together. I hear astronauts talk about referring to all their fellow humans as crewmates. So I see Jill hopping on there. I'm just about there, Jill. So just about there on the wrap up. So, you know, we got to the edge of the solar system. NASA also builds spacecraft to go up and look out deeper into space. And we get above our atmosphere, so we get good clear views. And this image, this is the Hubble Deep Field. We took the Hubble Space Telescope, aimed it at a narrow point of the night sky, about like looking through a straw. And in that one picture, very, very small picture, there's 5,000 galaxies. And if you extrapolate out to the rest of the visible universe, there's probably, well, we know there's trillions of galaxies, each with hundreds of billions of stars. And if you do the math, that means there's more stars than there are grains of sand on our entire planet. You know, and as I look at that, and I'll wrap up just a little philosophical, I kind of, that's overwhelming to me at times. I look at big structures. We've discovered Laniakea. It's one of the biggest structures we've seen in the universe. These lines are the paths of galaxies, and big galaxies like the Milky Way. There's probably millions more galaxies in here, but there's about 100,000 Milky Way sized galaxies in this picture. And we've been able to track their trajectories, and we see that they flow like this river. So if I had an address, it'd be Bremerton, Kitsap County, Washington, United States, North America, Earth, solar system, Milky Way, Laniakea. So I look at this view, then I kind of come back down in, and I look at our galaxy, and I come back in closer to our outer solar system, and I look at our inner solar system, and I get to my favorite planet, and then I get to my favorite part of my favorite planet. I'll take the Northwest, earthquakes and mudslides and volcanoes and all. I love it here. Then I zoom in a little bit more, and here's where I work. This is the UW Medical Center. On the fourth floor of this building is our NICU, our neonatal intensive care unit. And this is where we take care of some pretty sick babies. And I look at that baby. This is an actual baby from our unit, and I'm in awe. It took 13 billion years to make this baby, and it's just, in my mind, miraculous that this is here. All these elements had to form in stars in just the right way, collect in just the right amounts. Our human bodies have such an interesting mix of elements inside us. All those had to gather the right way, forming in our solar system. This planet had to hit our early Earth to make the moon, to give us a stable orbit. Our planet has to be at the right time in its life, that it still has a magnetic field. We have to be just the right distance from our star. Our star is big enough to protect us, but not so big as it destroys us. All these things have to line up. 13 billion years to make this baby. And then here's what we have to do. It got this far. I work in facilities at the hospital. I got to make sure it has filtered air and a reliable nurse call system to send emergency medical alerts if something goes wrong with that baby. We have to have social workers that are ready to help that baby on its transition home if that family's in a difficult situation. Nurses that teach skin on skin contact and how important that is for the early life of the baby. Nutritionists, janitors keeping the room clean and safe so the baby doesn't get infected. So much has to go so right. And we're a teaching and research hospital. So people are learning how to take care of other babies, learning how to help make babies healthy all over the planet. Our mission is at UW Medicine is to improve the health of the public, the whole public. And all that happens here. So 13 billion years to make this baby. And then it's up to us to seal the deal. My goodness, what a responsibility. But when we get it right, which we usually do, it's a pretty wonderful thing. So there's a lot of equations that help us understand how the universe works, speed and light and distance. But to me, there's one that kind of sums it all up. This ultimately leads to that. And I think that's a wonderful thing. Thank you. Sorry I went long.
Oh, Ward, that was wonderful. Thank you very much. I didn't see any questions, but I just have one, and I don't know whether you can answer it. But with the same, and maybe even making the tennis ball smaller, where do you think the edge of the universe would be? Maybe make the tennis balls into a spitball, like you said. Then where would the edge of the universe be?
So edge of the universe is a very tough question that a lot of people struggle with. And there are things that James Webb Space Telescope is going to help us look back even to the earlier days. So again, you look back in time, the further you go back. But edge is tricky to really know because there's only so far we can see. We know the universe is expanding at a rapid rate. So even though nothing goes faster than the speed of light, the expansion of space-time itself is going faster. So there's this point where the edge of what we can see as the universe gets further and further away. Like the furthest thing we can see is about 26 billion light years away now, even though that's further than the age of the universe, just because it's stretched out and the light has taken this long to get to us. As time goes on, we'll see less and less, and more will move further away. So it's possible, and these are almost as philosophical as they are physical questions because they're almost impossible at this stage to measure. The universe might be infinite. I mean, that is a very distinct possibility. Even how it's formed and how it's expanding, it might just be infinite going on out there. So yeah, edge of the universe is it's a complicated question that no one has a good solid answer to. And they're definitely hard to do on a scale model. So
well, thank you again very much. It was really interesting, and and your timing was just perfect. So thank you again, and we'll call it a night.
all right, thank you everybody, appreciate it.
Thank you.